All right, and we're back. Thanks again, everyone, for joining us for another Saturday morning science session with MSU Science Festival. Next up, we are joined by Dr. Zach Constan. Zach, welcome. Thank you so much for joining us this morning.
Thanks for inviting me.
So Zach, before we jump in, do you mind telling us a little bit about yourself and your work at MSU?
Happy to. So I work at MSU. I work at the National Superconducting Cyclotron Laboratory at Michigan State. We're also part of the Facility for Rare Isotope Beams. I'm also representing the Joint Institute for Nuclear Astrophysics. There's a lot of names and acronyms. What you need to know is we've got some really fantastic nuclear research going on in the middle of campus. My full-time job is public outreach and education. So it's important to me and to us that everybody gets to know what we do at a laboratory like that. Not everybody can just walk in and see it as much as I like. So we want to get that information out there for all the curious people on Facebook and wherever.
Awesome, great. Well, let's dive right in.
Cool beans. Yes, I have slides. I didn't bring any, well, I did bring a plant. Okay, so, but I didn't have any little plants. I'm a little disappointed. But I do have slides because I like to, some things I want to show you guys. Pretty pictures. So we're going to cover the entire history of the universe in about an hour. So buckle up, everybody. And here's all the people I'm representing today. And I'd like to thank a few folks who have helped me out with these slides in the past. But the universe has been around. It's 13.8 billion years. And we've had nuclei almost all that time. So, I think it took a couple minutes after the Big Bang. So essentially, we're going to talk about where all these things come from. And so, you and me, like where's all this stuff coming from? Where's that plant coming from? Where did the nuclei in this rhesus egg come from? I care very much about this. It's delicious nuclei, and I'm very curious. This is, in fact, what we do at our laboratory is try to understand where stuff comes from. So I'm going to tell you some things up front about how we have learned the things that we're talking about today. It's really important because a lot of times people maybe don't have quite the right idea, especially about the word theory. This is a good one. When you talk about theory of evolution or Big Bang theory, all that, we tend to use the word theory as guess, but in science, that's absolutely not what it means. It is an explanation, right? We see a lot of stuff going on around us, and the theory is a set of explanations that match what we're seeing. And, those theories like Big Bang and theory of evolution, we have been able to test those facts and again, repeatable. This is really important. And so the best theories that we have now have been tested over and over again. To this day, we're still coming up with new ways to prove Einstein's theories right, because there were a lot of things that he was able to predict that we haven't been able to measure until relatively recently, like gravitational waves, stuff like that. So, people have figured out in lots of different ways that, oh yeah, theory of relativity, nice job, worked out, okay? And so that's why we have things like theory of evolution, Big Bang theory. They are solid, they've been around a long time. Are they the last word? Maybe not. There might still be some evidence out there we haven't gotten that would, maybe support a different theory, but they're doing pretty good, and that's important. It's also important that we don't, theory is not a matter of belief. Either you accept the evidence that supports that theory, or you do not. You say that evidence was incorrect. So it's not a matter of belief. That's kind of important. So, like I said, we're talking about where matter came from. And of course, we're sitting in a solar system, on a planet, in a room, on a couch. All that matter came from somewhere, had to start somewhere. So that is one of the big questions that we have. Where did that matter come from? Also, we have a lot of other questions. There's a lot that we don't know. And this is what drives scientists, right? This is what we're curious about. So we're trying to figure out where the nuclei came from in this, other things too, but this peanut butter egg, I will save that until later. Everything's made of nuclei. Let's talk about that for a second. So you and me and everything, it's made of atoms. You might have heard of that before. And atoms, of course, are made of even smaller pieces. And I like to have a model to look at. So this is just a way to think about what the nucleus would look like. The nucleus is made of protons and neutrons. It's extremely small, so you're never going to see it. here's something to look at, right? Of course, protons and neutrons are green and white because I can make them anything I want them to be. And, those nuclei were made somewhere. So let's talk about it. Oh, here's another picture of an atom. It's really nice. This is a picture that we often show. It's called the Bohr model of the atom. Is it accurate? No. Real atoms are not red, white, and blue. They're green and white. Anyway, so actually no. But the point is, it's a model. We use models a lot. And this is a particular model that suggests, okay, maybe the atom is arranged in this way. And like I said, protons, neutrons, electrons. At our laboratory, facility for our isotope beams, middle of campus, we study the nucleus. And if you've been to MSU's campus, you might have walked right by us and not known it. Just to the right of this picture is the Wharton Center. Just to the left of this picture, about a block, dairy store. Okay, these are significant, really important places to know about at MSU. So FRIB is in the middle of that, and we happen to be a wonderful nuclear research laboratory. And of course, atoms that you and I are made of come in many different varieties known as elements. You might have seen the periodic table before. It's lovely, right? It's good for chemistry. And there's a lot of different elements. Well, of the elements you're looking at on this chart, some of them did not exist naturally. We made them up. And there are scientists who do that kind of work. That's not our work at FRIB, but it's interesting work, and people have discovered a lot of new elements. We're up to 118 now. And so we know, of course, where those elements came from. That's pretty straightforward. But, so if you're talking about nuclei that are not one of those elements, they're not artificial. They are naturally occurring. So something made them in the first place. So this is what we're really trying to explain, the origins of every single one of these things on this table. And it gets more interesting than that. Not just why does it exist, but also this is a little plot that kind of shows you the amount of each of these things. So this is the atomic number, so it's just different elements along this way. And this is the relative amount. And it's a lot, basically. This hydrogen here, we got tons of hydrogen, quite a bit of helium, very little lithium, beryllium, boron. Carbon, you might have seen it. You're made of it, right? A lot of elements, but some way more than others. So one of the big unsolved mysteries in, this is a beautiful word, nucleosynthesis, meaning the origins of the nuclei. Where do they come from? So not only where do they come from, but why do we have a ton of hydrogen and helium? This is more than anything else. And then like other stuff, we had a lot less. And when you get past iron, down here, it's like, whoa, it's way less. It's ridiculous. So whatever we come up with, whatever explanation we come up with to say, how did all these elements come about in the first place? We have to be able to, explain and predict, why should there be a ton of hydrogen? Why shouldn't there be very much gold and stuff like that? So these are the questions we're trying to answer. And it's a tricky business, but we're pretty good. So let's talk about what we know and the things we've learned. Here's the entire history of the universe, one slide. On the left is the origin of the universe, Big Bang. And then just time flows to the right. And so over this time, somewhere in that, nuclei were made. And they were made, in various times. The first nuclei ever made were really within the first few minutes. And so that's what we're going to talk about first. What happened right after the Big Bang? So according to the Big Bang theory, the predictions that it makes, this is really interesting. In the early universe, when the first matter came into existence, we're talking protons and neutrons, the theory predicts you'd have quite a few protons, not so much neutrons. So according to this picture right here, the relative ratio, right? We've got, for every 14 protons we've only got 2 neutrons. So there's a lot more of the protons. Now the thing is, you can have a lot of protons flying around. An individual proton is a hydrogen. That's what hydrogen is. But those neutrons, actually, they bind really nicely to protons. They tend to stick together very easily. So essentially, I've got 2 neutrons around. And if they happen to combine with 2 protons, what you've got is helium. 2 protons, 2 neutrons. So the Big Bang Theory predicts we had some neutrons available, and they combined with some protons, and they made some helium. But there weren't that many of those neutrons, so we couldn't make very many heliums. compared to all these protons that are sitting around. So what this predicts, according to the Big Bang Theory, is that there should be about 3/4 hydrogen, 1/4 helium by mass in the early universe. So if this theory makes that prediction, right, then we should look for evidence that says either that is not a correct prediction or it is correct. And so when we look at the oldest gases that we can find in the universe, that's what we get. It's a fantastic prediction. It's almost exactly 3/4 hydrogen, 1/4 helium. So the Big Bang has made a really good prediction based on what we know about physics. We would get this kind of relative proportions of those two elements. Now, here's an important point. I'm talking about looking at gas in the universe and telling how much hydrogen and helium is in it. That's a tricky business, right? You can't just go around like, I think it's got this. So the way we do that is called spectroscopy, which is a fancy way of saying we're measuring the light from that. Light's great. It goes all over the universe. It travels at light speed, obviously. And the light that we receive from stuff tells us a lot about it because, and this is really interesting, you look at this lovely nebula here. It's kind of pink. When you break that pink down, you end up seeing a few very specific colors. We got this red here. So basically, I've just taken the light, I'm spreading it out into, a rainbow essentially, but we're only getting little bits of that rainbow. I got a red, I got a sort of a light blue, darker blue, and over here, there's a purple. So that indicates that these are the energies that were created when hydrogen atoms just basically lowered their energy and shot out a photon. They shot out a bit of light. So we know from spectroscopy that every element actually absorbs and emits very specific colors of light. So if I've got a big gas of hydrogen and I look at the light coming from that, these are the very specific colors I should be seeing. I'm not going to go into the quantum mechanics because we don't have that kind of time. But this is what we should be seeing. And in fact, when you look at these gases, this nebula, you're getting just about 3/4 hydrogen, about 1/4 helium. If this is great, this specific light you're seeing is like a fingerprint for each individual element. So because it's unique, right? A fingerprint is unique for each person and it's unique for each element. So you can identify exactly what you're seeing. So, I mean, when I talk about how do we know what we know, looking at the light from stuff tells us an awful lot about the elements. Wonderful, wonderful information. So I can tell you, yeah, they're pretty much right. So if you go out and you see pink clouds of gas, hydrogen, that's just how the universe is. And another interesting thing, the Big Bang has made the theory has made a lot of predictions. And one of them is that, essentially the Big Bang encompassed the entire universe. And the Big Bang is just an expansion of that universe, which means that everything that was in the universe was in the Big Bang and still is, essentially. I mean, if you look in almost any direction, you're still looking at the same Big Bang. And the farther away you look, I don't know if you heard this before, the farther away you look, the older that light is, the longer ago you're looking. It's like time travel, essentially. It's just the farther away you're seeing, it took the light a long time to get to you, so you're looking farther back. So in essence, if you look far enough away in the universe, you should be looking back to the beginning. And so you should be seeing the Big Bang, light from the Big Bang, and we've seen it. Doesn't matter what direction you look in our universe, you look far enough away, you're getting light. It's not a lot, right? I mean, obviously the sky is kind of dark in general, but it's a little bit of light, and that is, we call it echoes of the Big Bang. We sent up this lovely WMAP satellite to actually observe this, and that's where we discovered this for the first time. We've gotten better measurements since then, but it was a big discovery, again, showing that the Big Bang Theory did a great job of predicting what you're going to see out there. So it's true. Okay, guys, Big Bang, we predicted it. We made hydrogen and helium. Awesome. Let's fill them in. Okay, only got 90 more elements to go. Awesome. There's a lot to fill in, guys. But the Big Bang, when you talk about hydrogen, helium, and how much there were compared to everything else. Well, they were the first things made. They were the only things that existed. At this point, the entire universe, when it comes to elements, hydrogen and helium. Of course, there are other elements now. And if you look at this little chart here, this shows you right after the Big Bang is sort of bluish here. And so right after the Big Bang, again, about 3/4 hydrogen, that's 76%, 24% helium, very good. Okay, that was then. This is now, this purple in the solar system. What do we got right now? Less hydrogen than we started with, more helium, and more of metals. This is one of the weirder things about astronomy is that they call everything, I'm going back, they call everything that's heavier than hydrogen and helium, they're metals. Not metals as you and I would normally think. They have a specific terminology. Fine. The point is, since the Big Bang, like almost 14 billion years ago, and now what we're looking at in our solar system, something has changed. Less hydrogen, more helium, more of everything heavier. So something is happening between then and now to change the nuclei. And it's reactions, nuclear reactions. There are lots of different kinds. Particle capture, basically something sticks onto a nucleus, makes it a little bit different by just adding on a neutron or a proton. Radioactive decay, where a particle actually comes out, and there's lots of different kinds of ways that can happen. And there's nuclear fusion, where several different nuclei stick together and build up to make something much heavier. So there are ways that nuclei can change, which will result in changing elements. And so if this is one way that you can make new elements from that hydrogen and helium that we started with, then what we really need to know is, where's that happening? Like, where can we make the new elements? Where are these reactions possible? And so, I showed you the Big Bang period here where we made the simplest elements, but we are now in the age of stars. Stars are doing nucleosynthesis. They're making new elements. So let's talk about it. Here's your most familiar star. You should know about this one. Sun is right there. It's pretty obvious. And it is generating a ridiculous amount of energy. Just crazy amount of energy. So it's, one thing you could wonder and ask about is like, how? Like, where's all that energy coming from? And this is important to note. The sun has been around, the solar system has been around about 5 billion years. We're pretty good at predicting that. And so if you want to say how long, how much energy is it used, basically it's burning fuel. You could think of it that way. And so the luminosity, how much energy is coming out, is a measure of how much energy is coming out per time. Well, it's a ton, we know this. But basically, if you want to know how long it'll last, then you need to think, how much fuel do I start with and how fast am I using it, right? So, right, if you're driving a big gas guzzler, you're going to run out of gas faster. That makes some sense, even if you have a big tank. So you need to think about this, right? The sun has been burning like this for a very, very long time. Obviously, it's a really massive thing, so it's got a lot of fuel in it. But so let's think about how it could be generating that energy. One way we know to make energy, and we do this, is burning coal or natural gas. And by burning stuff, of course, energy comes out. Thing is, if the sun was literally made of just coal and it was just burning coal, and that's how it made the energy that you see shining off of it, the total, with the amount of fuel that it had, the total time it could burn, 10,000 years. That's all it would make. And like I said, the solar system's been running much longer than that. So we're pretty sure it's not burning something, right? It's not like we think of burning wood or coal or natural gas. That's not what's going on here. So something else must be going on. And I'm just alluding to things I've already said, right? Nuclear reactions. So the amount of energy available in the core of the sun to burn at this rate, to shine this much, we think it should last about 10 billion years. That's good news for you and me, trust me, okay? And of course, the reason this works, you might have heard of Einstein's E equals mc squared. Basically, the sun, in the process of fusion, and we'll get to that, is changing mass, m, into energy, E. C is the speed of light. It is a big honking number. Trust me on this. So when you multiply mass times a big hunk of number, and that's squared, so you get to do it twice, a tiny, tiny, tiny amount of mass creates a ridiculously large amount of energy. This is the most efficient way to make energy in the universe that we know of. So what's going on here is, yeah, it can shine like crazy because the mass that it's using is generating a ridiculous amount of energy. So it'll last a long time, much longer than burning coal. So fusion, that's a good deal. So the reason that fusion can happen, now it doesn't happen often because generally you're talking about trying to stick nuclei together. Well, nuclei are made of protons. Sorry, my protons are white, these are yellow, just go with me. Protons are positively charged, and basically equal charges repel. You might have seen, magnets, you try to put two north sides together, they repel each other. Well, same with two positive charges, electric charges, they will repel each other. They don't want to get close. So it's really hard to do fusion because those things don't want to get close together. And they have to get close enough to stick. So they repel each other. They bounce off, basically. Now in a star, you got ridiculously high temperatures, right? It looks like it's on fire. The thing at the core is like, 10 million Kelvin. It's a crazy high temperature. And temperature is basically an indication of how fast are things going. That's what temperature really means. So the matter in the sun, because it's so hot, is going extremely fast. So if I try to send these two together, pretty slowly, they're going to bounce, they're going to push each other and bounce off. But if they're coming at each other ridiculously fast, they're not going to have chance. They're going to overcome that repulsion and stick together and make something new, bigger. This is fusion. I'm taking nuclei and stick them together. And once they get close enough, the nuclear strong force, which is a whole other story, but trust me, is going to make them stick together, even though they repel each other. So you can build a bigger, heavier element through fusion. So right now, our sun, mostly hydrogen, because that's what the universe was really, is taking those four hydrogens and they're fusing them together. What they're ending up with is helium, two protons, two neutrons, also shooting out positrons, that's antimatter, nice stuff, and neutrinos, wacky stuff there. Now, the reason that you're getting energy in this process, from going from protons to helium and all this other stuff, the total mass of the four protons is more than the total mass of all this stuff left over. Like I said, you're converting matter into energy, and you're getting a ton of energy out. In this case, gamma rays. It's just really high energy light. And that's where the energy is coming out. That's why you can produce a ridiculous amount of energy for a very small amount of matter that you changed. And we, of course, see the light coming out. We also see the neutrinos. That's another way you can really tell that fusion's going on in the sun. We can detect those neutrinos. It's really ridiculously hard, but they come out, they fly straight out of the sun. They fly right through the earth all the time. You have, trillions of neutrinos flying through your body right now. Don't be worried, it's fine. But, that's one way we can tell that fusion is going on there, because we're not going to go to the core of the sun and observe this. It's just not safe. So we look at the neutrinos and we can tell. So the sun, of course, is burning, but it is going to run out of fuel eventually. So the way the sun kind of works, and all stars really, is that the pressure and temperature generated by this fusion in the core is counteracting the gravity, all this matter of the sun pushing together. So basically the gravity of the sun would collapse it, except for the pressure of that the fusion is generating, pushing back out. That's why the sun kind of hangs out right there. It's not really changing very much. It's not collapsing, it's not blowing up. These kind of are in balance. But eventually we're going to run out of fusion, the hydrogen in the core, we're going to run out. At that point, of course, there won't be new pressure being generated, so the star will start to collapse. This is going to happen to our sun. You still have about 5 billion years. So again, don't worry too much. But of course, as the star collapses, essentially it's going to heat up the core even more. It's going to get so hot that helium fusion can start. Those helium nuclei were repelling each other even more strongly, but now that they're going even faster, you can actually get fusion. And you can start fusing hydrogen in this little region around the core where it was never quite hot enough to do the fusion. Now it is. So suddenly, I stop fusion, I collapse, and now I'm starting two different types of fusion. I'm going to get a lot of energy, a lot of pressure, and that pressure is going to be so much it overwhelms the gravity and pushes the star way back out. This is called the red giant phase. You might have heard of this one. And so the sun is going to swell up and become huge. At some point, it will be big enough that it will actually get out to the orbits of Mercury, Venus, Earth. It's going to swallow our planet at this point, again, 5 billion years in the future. And eventually it will run out of that too. So, but here you go. This is great stuff. If you can fuse helium into something heavier, this is, I love this one. So, I mean, we made hydrogen and helium from the Big Bang. We haven't even talked about making anything new. But essentially, and here I'm gonna aim you guys down here for a second. I want you to see what I'm doing here on the table. So I've got 3 helium 4 nuclei right here. And they each have 2 protons, 2 neutrons. So if you're in a star where there's an awful lot of fusion going on between helium, if you stick 2 heliums together, what you end up with is beryllium-8, which is actually radioactive, and it splits back apart right away. So we've not really accomplished anything. Too bad. But if you get lucky, and there's a lot of heliums flying around really fast, 3 helium 4s can come together at once. And you make something much, much bigger. Now I have 6 protons, 6 neutrons. This is a carbon-12. You are based on carbon. This is where carbon comes from. That is, something new. And so this, we call it the triple alpha reaction, but it makes carbon-12. So there's the origin of life. Pretty good stuff. So the sun can do this. And higher mass stars can fuse even heavier stuff. Hey, I made carbon. Good job. Well, what if I tack on another helium? I can make an oxygen. Well, I got oxygen. What if I tack on, you just need really high temperatures, but maybe I do. Let's tack on a helium, neon, et cetera, et cetera. If you just have a really massive star, tons of energy, tons of, particles flying around, you can just keep building up heavier stuff. There's a point where you stop, of course. So in essence, eventually, you're going to be burning a lot of different things, fusing them. And low mass stars like our sun, are going to really stop after making, helium or carbon. So carbon's pretty much the end point for our sun. Really high mass stars, you can fuse all the way up to iron. So basically, if you want to explain the elements between helium and iron, that's where they're coming from. That's the fusion that's generating those elements. So good. We filled in a few more. Big Bang took care of 2 of them. Now we've added a few more. Fusion, which we know happens, can fill in this part of the chart. Okay, still got a long ways to go. I told you iron is the end, right? We can't make anything really heavier than iron through fusion. And there's kind of a long story, but basically the reason that fusion works is that it releases energy. And essentially, from fusing from hydrogen to helium, you get a ton of energy. And when you go from helium to carbon, you get some energy, and helium and carbon and oxygen. Basically, going down this chart, your energy is coming out. So fusion is basically powering the star. If you get to iron and you try to fuse to something else, instead of going down, you're actually going up in this little curve here. So instead of gaining energy from that fusion, you're losing energy. So that's not going to power the star. It's actually going to eat up all the energy the star has. So iron is a dead end. If you're going to fuse in a really massive star and you're just doing fusion, iron is what you get. That's as far as you're going to go. So now we've explained elements up to iron, but all this stuff heavier than iron absolutely cannot be explained by fusion. So when you look back at this chart we have here, we explained pretty well, yeah, hydrogen and helium, easiest stuff to make. Big Bang made them. We've got tons. And then stars have been making all this stuff here in the middle. These no, and we'll get back to those. But this is how stars have fused into these things. And like I said, iron is as far as they're pretty much going to go, maybe a little nickel. So that's why it kind of drops off like crazy over here. So we kind of understand where these came from, and we kind of understand how they could be made. But actually, this is a really important question. And this is an unanswered question. Why do we even have these elements at all? what could possibly be making these elements? Because fusion that we understand doesn't do it. No, it's unanswered, but that doesn't mean we don't have ideas. We don't have good ideas. And we do. I'm going to show you. You tuned in for it, right? So if you're going to make something heavier than iron, you can't do fusion. Of course, it would be really hard anyway, because trying to stick another proton, positively charged, onto all this other stuff, right? It's going to repel very strongly. It's going to be ridiculous. Neutrons don't have a charge. They're neutral. So, is there anything keeping this from going in? No. It's easy for this to stick on. So, while adding more protons is not really an option beyond iron, adding neutrons seems like it's reasonable. Seems like it could be done. There's a problem. If you have a neutron hanging out by itself, it is radioactive. It has a short life, about 10 minutes, as you can see right here. So literally, if I want to have neutrons to stick onto a nucleus, we don't have them lying around. Because if they are lying around, they're radioactive, and they end up decaying and becoming a proton. Well, okay, so great. We had a solution. Just stick some neutrons on instead. But we don't have neutrons. So something must be going on, because if something did make neutrons, if there were new neutrons made, maybe there's something. But right now, in general, you don't have them just lying around. Well, here is the constellation Orion. You might have seen this one before, right? The belt, very famous, real easy. Here is the star Betelgeuse, or Betelgeuse. I mean, you can pronounce it various ways. I like Betelgeuse. That is from the Arabic, meaning literally armpit of the Great One. That's a nice trivia fact for you. And Betelgeuse is a ridiculously massive red giant. It's a red supergiant. It's crazy. And what we believe is that when you have a red giant or red supergiant, there are nuclear reactions that can go on inside that environment that make loose neutrons, that give you neutrons available to do that reaction, to add neutrons onto a really heavy thing. So, here's the deal. If there are neutrons made in specific reactions in a red giant or a supergiant, then they could stick onto a nucleus, right? So here I've got an iron nucleus, maybe that I made from all this fusion, and my star's getting ready to die, but I made a lot of iron, good for me, and maybe I can add a neutron onto there. Well, you're going to end up making something that's radioactive, if you do this enough times anyway. But iron 59 is in fact radioactive. And the way that iron 59 will change is by literally switching the neutron that we just added into a proton. This is a specific kind of decay called beta minus. But long story short, it converts a neutron into a proton. You can only do these under special circumstances, but it does. And so now, the result of me adding neutrons on is I ended up getting more protons. Well, that makes a heavier element. I got something new now. Instead of just iron, I got cobalt. So by adding neutrons on, slowly, that's why this is called the S process. S is for slow. If I'm adding neutrons on in a red giant or supergiant, I can make heavier elements than I had before. So, awesome. And then maybe that new stable element absorbs a neutron. And maybe that happens again, and maybe I can finally end up making something even heavier. If I keep doing this, adding neutrons, decaying, adding neutrons, decaying, I keep going up the elemental scale. Now, again, how do we know? I keep telling you, well, there's probably some reactions in there that are making neutrons. Remember, we're looking at the light from things to tell what's going on. And here's some spectroscopy from a red giant, meaning that I can, from these specific lines of light, obviously this is not in full color, you get, it's just, there's light there. This light is telling me that in this star is technetium. This is my favorite element because it is the only element, naturally occurring, that doesn't have a stable isotope. Meaning, we don't have technetium lying around on Earth. The only way we got it was by making it. So it's why it's called is technology, basically. Technology made technetium for us. But we can look out and see that star. That star has technetium, right? And now it has a lifetime, 4 million years. And the star we're looking at was billions of years old. So the thing is, even if that star formed at the very beginning with technetium, who knows where that came from, that technetium would have decayed and be gone like long time ago. So if there is technetium in the star now, the star must have made it. And the only way it could have really done that is by adding neutrons on to iron or something later. But eventually you're going to get up to technetium. So this is one nice piece of evidence that we have to tell that the S process, slow neutron capture, just sticking a few on, letting it decay, is making some of these heavier elements, including technetium right there, number 43. So hey, the S process fills in a little bit more. We're getting there. Obviously, we're not done. There's still a few elements left that we have not explained. Where are they coming from? So we have more work to do. But you might have seen a supernova, or at least heard about it. I'm sure you haven't seen a supernova. But essentially, at the end of a very massive star's life, like Betelgeuse, for instance, that star, when it finally really runs out of gas, is going to explode. Really massive stars blow up. And we're still trying to really understand that. But in a supernova, essentially, there's an awful lot of energy released and a lot of particles flying around. And maybe some reactions could happen that haven't been happening before. Maybe this is a nice breeding ground for some new nuclei, some elements that we haven't explained yet. Another nice place, I mean, we're talking about trying to add neutrons onto a nucleus. Well, only recently we've actually gotten some evidence that neutron stars merge. So a neutron star is mostly a giant ball of neutrons. And by giant, I mean like size of Lansing. It's about the size of a medium city, really. It's just a huge ball of neutrons, like a big nucleus. And some neutron stars out there are close enough to each other that they do this beautiful animation, that they actually merge and become, something new. A lot of things are flying off here. But basically, this is another environment where there's a ton of energy and there's a ton of neutrons flying around. Maybe you could do neutron capture faster. S process, slow neutron capture. Now we're going to talk about R process, rapid. These astronomers are great at naming these things. Okay, so here's the deal. Let's imagine we had our iron 58, which is nice and stable, and we tack a neutron onto that thing, okay? And now it's radioactive. It's going to decay, but it doesn't have time to decay because there's so many neutrons flying around that another one sticks onto it. Now I got iron 60. That doesn't have time to decay. Whew, okay, finally we get to the point where it's so short-lived, so radioactive, it's going to decay before it catches another neutron. There's a lot of neutrons around. And then it decays, again, it turns a neutron into a proton, goes up the chart. But now this is going to capture some more neutrons. So this is going to be happening so fast, it will be possible to make some nuclei we've never made before. Okay, this is a really cool animation. This comes from Hendrik Schatz. He's one of the faculty at our laboratory. And basically what this is each row in this chart here is a different element. So we're starting down here, the bottom row is iron, and so everything above that is something heavier. And essentially, this is a simulation of a supernova saying, okay, if I let my star explode, I got a lot of this iron here, then assuming let's just make some predictions about how many neutrons are going to be attached to that and how fast that's going to happen. And of course, those will decay. So basically, they're going to add neutrons, which means they're going to go to the right. That's going to the right on this chart. And then when they decay, they're going to go up and to the left. So this model simulation here is trying to predict in a supernova what will be made from this iron when I start sticking neutrons on. And they'll be really fast, so it's going to be rapid. A couple things I want you to know. The colors of the different squares, that's telling you these different elements. If you have red, you have a lot. Blue is not very many. Here's the temperature in the core of the supernova. That's 1.5 gigakelvin. Trust me, it's really, really hot. And then the time is the time after the supernova has exploded, basically. So let's let her rip. See what happens in this supernova. Within 1 second after it explodes, so many neutrons flying around so fast, you make all this stuff. So many different nuclei. So many elements heavier than iron. Eventually they will decay. They're going to decay back. You see these black squares, these are all stable nuclei. So eventually, they're going to get back to something that's stable, something that's not radioactive, and then they'll be done. They'll exist much longer. So essentially, by letting this star explode, we've turned iron into all these other elements. We filled in our periodic table in large part. So we think this rapid neutron capture process in a supernova or a neutron star merger, those that seem like the likely locations for this kind of stuff to go on, could result in these really heavy elements, the ones beyond iron. Fusion's not going to cover that, but they do exist, and our prediction is it's got to be neutron capture processes. And the things that we've learned, especially in the last decade or so, have really pointed to, yeah, it seems like this is probably happening. And we're pretty sure neutron star mergers are a big part of it. Thank goodness for detecting gravitational waves that let us know it actually happens. It's wonderful stuff. So we can fill in our process, rapid neutron capture. That's covering just about everything else. But even then, it's not quite everything. And now we're thinking there's more capture processes, maybe an intermediate, so not a slow capture, not a rapid capture, sort of middle, medium capture of neutrons. And maybe, hey, there's a place where you can capture protons instead, just stick those on. Again, we said it was really hard, but maybe there's a place you can do that. So this is what astrophysicists and nuclear scientists are doing in large part. This is one of the big questions we're trying to answer is like, how do we make sure we understand the origins of all these? And I did promise we'd get back to lithium, beryllium, and boron, not made in the Big Bang, not really, not made in fusion, but we think particles flying around in the universe, we call them cosmic rays, when they're running into nuclei, they're breaking them and making these lighter elements. It's unlikely for that to happen. The universe is big, empty space, but it does happen, so we do have some lithium, beryllium, and boron. So where did we come from? Where did our solar system come from? Where did this peanut butter egg come from? Stars are out there. They're doing fusion. They're creating heavier elements. They're exploding. They're doing neutron star mergers. They're creating even heavier elements. And of course, the gases left over after these reactions end up making new stars. So the universe basically has a system where it's just continually enriching itself with heavier and heavier stuff. So in the time since the 14 billion years ago, the Big Bang, between then and now, we've gone from almost all hydrogen and helium to a little bit less hydrogen, a little bit more helium, a little bit more of everything else. And as the universe continues, it's going to keep making new stuff. So, and that's cool because all the elements that we use for life, this is where they're originating. I mentioned that I'm part of GINA, Joint Institute for Nuclear Astrophysics. This is basically an organization that gets scientists together and they say, okay, hey, astronomers, you're looking at what's going on out there. You're seeing, we have a lot of this element and not much of this. Hey, you're seeing these beautiful nebulae. How do we explain those things? And the nuclear theorists are saying, hey, I think maybe, two neutron stars merge and maybe you get these rapid neutron captures. Sure, why not? And then there's experimentalists like the researchers at EFRIB on campus, and they're doing this kind of work. Okay, the theorists make these predictions. Can this actually happen with nuclei? Do they do this kind of stuff? And from what we learned, can we make a prediction about what we should see out there? So between the astronomers and the nuclear theorists and the nuclear experimentalists, together we're trying to answer this big question. Where do the nuclei come from in our universe? It's a really, really cool mystery. Now, I want to say one more thing before we're done is, I mentioned we got this wonderful lab in the middle of MSU, and that lab's actually been there a long time. We have a couple of cyclotrons. Our lab has been there since the 60s. We built those cyclotrons in the 80s. We've been doing fantastic nuclear research on campus for decades. And our laboratory today is one of the top 3 in the world. It's a fantastic laboratory for studying rare radioactive nuclei. So this is kind of a map of it. And this is where the action happens in this one room, 450 feet long. Basically what we do, we accelerate nuclei, smash them very hard, make something weird, rare and radioactive, and study that. We're trying to study nuclei that don't exist on Earth, right? Stars make them, but we don't have them here. So if you want to do that, you got to make them yourself. And that's what this laboratory does. That said, we're top 3 in the world, but we're not good enough. There's a lot of nuclei we want to measure, especially in the R process. We think there's a ton of nuclei that the R process would make, and we can't make them ourselves. We can't study them ourselves. How are we going to get there? We're building a bigger one. We need to break more nuclei, basically. We won this project. It's a $730 million project, mostly funded by the US Department of Energy. And with that money, we are building the facility for rare isotope beams, replacing the cyclotrons that we have with a 400-yard long linear accelerator, 35 feet underground. This new accelerator is going to do 3 things. Number 1, smash harder. Number 2, smash more. Number 3, make us the best place in the world to study these kinds of rare nuclei. We will be able to do things nobody else can do. And so that's the excitement, right? There's a lot of things we've wanted to learn for decades that we've just never been able to make and never been able to really study. And this laboratory is going to make it possible to learn about those nuclei. That's why you hear about EFRIB in the news. It's a big deal because not only is it a huge project, but it's going to push the limits. It's going to discover entirely undiscovered territory in nuclear science and astrophysics. So this is a nice little chart here. This basically shows all the different kinds of nuclei that our current laboratory with the cyclotrons, that's the C. These are the kinds that we've made and studied. And there's like 1,000 of them here. It's pretty good. I mean, we've studied a lot of nuclei. Here's the R process. We think that in the rapid neutron capture, you make these nuclei. Have we studied a lot of those? No. EFRIB is going to be more like this. Now you can see we will finally have access to an awful lot of these nuclei that in general only exist in stars when they're exploding or neutron stars merging or something. We've never really been able to understand them and learn about them. Finally, we're going to have access and do these experiments. Can we do them all? No. We think the R process goes way out here. But EFRIB is going to push those limits. It's going to let us do things that we've never been able to do and get a better handle on where did this peanut butter egg and everything else come from, which is great. A couple advertisements. We have a wonderful laboratory. We want you to know as much as we can, as you can. Of course, when you can go there, Impression 5 Science Center in downtown Lansing has an exhibit about us. It's called Smash, because that's what we do. There is a video game about our laboratory. If you like breaking nuclei on your phone, it is called Isotopolis, and it is free. You can download it now. We have camps. We have, all kinds of other things. I am going to actually bring my little ad up here, adjust the screen a little bit. I'm going to stop sharing. So while I'm answering questions, I'm just going to be advertising that this is the website you can go to get a lot more information about our lab. We got YouTube videos. We got that game. We got a virtual tour. And my email's on here too. You want to ask me questions? Ask me questions. Because I love bragging about our laboratory. It's fantastic. Thank you.
Thank you, Dr. Constan. And we do have, I'm going to take our youngest viewer's question first. He's 7. His
Awesome.
name's Miles, and he wants to know what is radioactivity? What does that mean?
Yes, okay. I mean, let me tell you, my job was to cover 14 billion years in an hour, and I had to skip over a few things. So here you go. Radioactivity is basically, there are some nuclei that have too much energy. They have extra energy. If you've ever ridden on a roller coaster, at 7, we'll see. But basically, when you start really high energy on a roller coaster, you go down that ramp, you get going really fast. Basically, you have a ton of energy and then you kind of fall. So some nuclei have a lot of extra energy, and we call them unstable, and they want to get rid of that extra energy. They want to get to a lower energy, just like you go down the track. They want to lose some of that energy. Radioactivity is this nucleus is going to shoot out a particle or a light or something to get rid of some of that extra energy, basically. And there's lots of different kinds of radioactivity. Some nuclei literally just shoot out a proton. That's it. Some just shoot out a neutron. Some change one of those neutrons into a proton and shoot out an electron. Or sometimes you get a proton to a neutron and you shoot out a positron. That's antimatter. And sometimes you shoot out gamma rays, high energy light. So basically something's got to come out of the nucleus. We call that radiation, if you've heard of that. Radioactivity means this thing is going to give out radiation at some point. Some are faster than others. Some radioactive things last much longer, and that's half-life is what we call it. And so some will last for less than a billionth of a second, and some will last for millions of years, but they all have a little too much energy, and they're going to get rid of it by shooting out something.
Awesome. Thank you for that. Then Julie had a question. Where can I find that theoretical animation of nucleosynthesis in a supernova?
It's pretty sweet, isn't it? It's a really simple animation. Email me. But if you do a Google search, you look for our process animation, you'll probably find some, because there's a lot of really great theorists out there who are just generating these really big, complicated simulations of that process. And so if you want to, see what they've made, because people always make it really cool, like those animations of the neutron stars merging and thing. Yeah, look for our process. You'll probably find stuff. Or you can, go to our website. There's probably something there too.
Awesome. And then Felicia wants to know, is the implication that there are fewer odd-numbered elements since the helium atoms that fuse each have 2 protons?
Yeah, you noticed that, did you? That's a really good job. Like, that's observant. Well done. So here's a really funny thing about nuclei. This is one of the things we've been trying to understand, is that they want to be low energy, like I said, and high energy means they're going to give off radiation. One of the things that makes a nucleus low energy, it likes to pair up stuff. Pairs of protons, pairs of neutrons, good. Even numbers, they like, for whatever reason. Odd numbers, not so much. So in the end, it is a little bit easier to make even numbered elements than odd numbered. It's a wacky thing about the way the nucleus works.
All right. And then we have Sarah wants to know what happens at the extreme limits of the R process. What happens with super heavy elements? How weird can it get?
It's pretty weird. I mean, what's great about the R process is if you have enough neutrons flying around, you're going to end up you're going to add on neutrons until you get to the point where if you try to add another neutron on, it won't stick. We call it drips off. It falls off. It just never binds onto the nucleus. And this is something that we've been trying to understand in nuclear science. We call it the drip line. Basically, where is the limit? If I have a particular element, this is carbon, how many neutrons can I add onto there before they just start falling off because they won't stick at all? For a carbon, we know that. I think it's 16 neutrons. You can stick 16 neutrons on this and they'll still stick, at least temporarily. But you had a 17th? No. For the lightest elements, we know how many neutrons you can add on. For stuff heavier than oxygen, I think we now may know neon. But like for almost all the elements, we don't know. And so if we want to understand the R process, we want to know how far it can go before adding on more just doesn't do anything. We need to know where that limit is. And thankfully, FRIB is going to help us explore that limit a little bit when we got that new accelerator. I didn't mention, it's coming. We're aiming to be done next year. By the end of next year, we're aiming to have that new accelerator running and doing world-class rare radioactive nuclei research. 2022 at the latest. So students who are with us now, if you come to Michigan State, you could help us run the best rare isotope lab in the world. Just point that out. Okay.
And you just answered a question from Caleb. First, he said, thanks for sharing your passion. And he wanted to know, does the current situation impact the FRIB schedule at all?
Yeah. I mean, so we basically have had to stop doing experiments, which hurts because that's our life. That's what we do. And we've had to stop construction, at least temporarily. Construction has been coming along very well. We're trying to do the best job that we can. And so, basically we've always said that we wanted to be done by 2022, but we were trying to do such a good job that we'd be done a year early, 2021. So we're keeping my fingers crossed that we can still be done by the end of next year and doing world-class research. But until then, we will keep doing really excellent world-class research with the current laboratory and hopefully have it up soon.
And then he also wanted to know what research is going on currently at LHC laboratory.
So the Large Hadron Collider, LHC, it's at CERN in Switzerland. When people hear about accelerators and big, physics laboratories, that's what they hear about generally, because it's the biggest, baddest accelerator in the world. It's 17 miles around. And what they're generally doing there is two beams of protons coming at each other as fast as they can. And we're talking 99.999999% of the speed of light. It's pretty darn fast. It's a lot faster than we get. We get to, not even half the speed of light. So these things are coming at each other so fast that when they hit, I mean, basically it's like breaking, but it's more like, I showed you E equals mc squared. Matter can turn into energy. And it actually works both ways. The energy of this collision is so much that particles are created out of that collision. And basically they're trying to study at the LHC the most fundamental, simplest particles. Protons are not the smallest thing. There's quarks, even smaller than that. These are made of quarks. And there's things like the Higgs boson, you might have heard of that. There's a lot of weird, very fundamental, tiny particles. I know things are made of atoms. Atoms have a nucleus. Nucleus has protons and neutrons. It keeps getting smaller. But that's what they're trying to study is what are the most fundamental basic pieces of matter. And to get that kind of stuff, they have to hit protons together as hard as they possibly can. We don't have to hit quite that hard to make the weird nuclei that we're making, but so they're doing a different kind of research. It's called high energy physics, particle physics. They are the best laboratory in the world for that kind of research. They beat out Fermilab here near Chicago. They used to do the best research in that type. And, so that's their business. But of course, we study rare nuclei, radioactive nuclei. And so we're not competing with them, which means, we're going to be the best at that.
Awesome. Well, I think our time is almost up. I'm going to throw it back to Catherine, who can tell us maybe what's happening later on next week. And Dr. Constan will be around for a few minutes to answer some of your questions that you might still have. We didn't get a chance to get to them all. So thank you for coming, Dr. Constan.
My pleasure.
Yeah, thanks, Zach. And thanks, Roxanne. And thanks to all of you. Thank you so much for joining us for another Saturday morning science session. We are continuing to do these programs every Saturday throughout April and also throughout the summer. So if there's a topic that you're curious about, if you want to learn more about, please feel free to shoot us a message on Facebook. We'd love to hear from you as we start designing our programs throughout the summer. So again, we have Saturday morning science programs on Saturdays. You can find all the most up-to-date information on our Facebook page. If you just go click over to our events section, you'll see what we have coming up. And we're also doing Science After Dark programming on typically Wednesdays and Thursdays, Mondays and Wednesdays every week. So coming up on Monday, the 20th, this upcoming Monday, we are going to be joined by Dr. Mark Ramers from MSU, who's going to be talking about the mysteries of the human brain and the Brain Project. So excited to learn more from him. Yeah, so thanks again for joining. We look forward to seeing you again soon.